Hello. So I will be making a series of videos to help explain and apply the formal definition of the limit, the epsilon delta definition of a limit. This is important as it really formalizes the bedrock of calculus and moves us past our simple intuition of what a limit is. But that's actually a good place to start for now, our intuition. So let's say that we know that the limit as x approaches a of f of x exists and it equals L. So let's look at a graphical example to actually visualize this. So here are x and y axes, and we will draw the graph. You can have like a point discontinuity. Okay, so let's say that this is our graph, and over here we have our value a, and over here on the y-axis we have L, which remember doesn't necessarily have to equal f of a. L, a. So our intuition tells us that this limit statement over here is basically saying that as we pick x values closer and closer to a, as we kind of move closer to a, but not actually equaling a, the corresponding f of x values get closer and closer to L. The arrows start moving closer and closer to this L value over here, right? So now the problem is, how do we actually formalize what this closeness actually is? So this is what I will be covering. To define this closeness and approaching behavior we normally talk about with a limit, we can start by kind of defining a distance around L and A that we simply label as sufficiently close. So let's say we allow an epsilon distance around L, or we allow for epsilon window, meaning epsilon units above L, like here, and epsilon units below L around here. So these two distances are epsilon and epsilon. And that we allow a delta window around A. So let's say around here and here, so delta units below and delta units above A. So within these distances we defined, so basically within these distances we are sufficiently close. So now the question is, what should be the relationship between these two distances? How can we kind of use these distances in order to make a sensible definition of what a limit should be? So we can actually kind of get an intuition for these distances and the relationship by looking back at a regular limit statement, right? So let's say we have the limit as x approaches a again of f of x equals L. And again, all this is saying is that as x approaches a, f of x approaches L, right? Meaning all the limit statement is saying is that if we are sufficiently close to a, then f of x becomes sufficiently close to L. So as the distance around a is less than delta units, but remember, the distance can't equal 0, as the limit never defines the behavior at that particular a. It only defines it as the x values approach a. So basically less than delta. Then this implies that all the corresponding f of x values derived within that delta window must be less than epsilon units away from L, if that is the true value of the limit. So this boils down to the distance around a being greater than 0 but less than delta. So the distance around a, so that x values around a must be greater than 0 and also less than delta, which remember is defined as being sufficiently close. And this implies that the corresponding f of x values are sufficiently close to L. So the f of x values are sufficiently close to L. So the distance between them is less than epsilon. And this is implication. So this is basically saying with this picture. Okay, so this picture, let's draw the actual, the full extent of these windows. So uh, the epsilon window is like this. It's within this big region, and then the delta window is right here. So one interesting thing we note is that whatever x values we choose for within this delta window over here, right? Whatever x values we choose within this delta window, we always get corresponding f of x values within the epsilon window. So you see that the f of x values are always is basically always greater than the lower epsilon bound and less than the upper epsilon bound. See over here, it never kind of crosses. It never becomes greater than or equal to epsilon units away from L. So this means that basically we are kind of defining this this how shall I say this sufficiently close. We were getting so basically we are getting at defining this. So now essentially our job is to define kind of the nature of epsilon delta. So basically, what possible values can epsilon and delta be? So obviously, epsilon delta, well, maybe probably not obviously, but they should actually be both greater than 0. So first of all, we are obviously talking about distances. So obviously, epsilon and delta must be non-negative, so at the very least greater than or equal to 0. Is what it should be, but for now we have this. For now we say that they're both greater than or equal to 0 because we're talking about distances, but they also shouldn't exactly be 0 because again, we are trying to encapsulate this approaching behavior that the limit possesses. X approaches A, f of x approaches L, but they are never actually they are never actually x never actually equals A, if you see what I mean. Thus, the epsilon and delta windows must be greater than 0. So instead of greater than or equal to, it should really be greater than 0. The distance, it must be essentially positive. One final point is that the implication holds true for all. So for all epsilon greater than 0 and some delta greater than 0. So in order to better understand this and why epsilon is for all, why delta is some, we are essentially just playing a game, right? Making a proposition that the limit exists and is equal to this L value. So we need to prove that for however small the epsilon window is, however small of a tolerance or error we allow around this proposed value L, there exists a delta window from where the x values always satisfy this above proposition, right here. So they always leads to essentially sufficiently close f of x values. So let's complete this. So for all is here, and this is some. So again, let's go back to the graph to get a better understanding. So we have the graph, and we have our function once again, a, l, and let's say that our epsilon window is this, our delta window is this, and then we can see right off the bat that whatever f of x values we derived from within our delta window, we always get sufficiently small f of x values, right? The f of x values always lie within this range, or sorry, sorry, it's actually this range over here. It's always within this epsilon tolerance. And then it's not only that epsilon tolerance, it's for whatever epsilon tolerance is chosen. So it can also be here, LA. It can also be something as small as like here. See, it's much smaller. We can just choose whatever correct delta window would work. So we can just choose an extremely small delta window like here and here. And then we see that once again, we find that whatever x values we derive from the delta window, we always get f of x values that are sufficiently close to this limit, sufficiently close to comply with the above proposition, right? We are always here and here, and the magic with this is that this works for whatever epsilon, no matter how small it gets, no matter how arbitrarily small it gets, how arbitrarily close the corresponding f of x values gets to L. So this is why this is really a very sensible definition of what a limit truly is. And so let me write the actual definition all in one great big line. We will start with what delta and epsilon values we allow for. So it's again for all epsilon greater than 0, there is some or there exists at least one delta greater than 0 such that ST stands for such that the proposition holds. So what is the proposition? It's that the values, the x values around a are less than delta, but they are not, it's not equal to a, x is not equal to a, implies that the corresponding f of x values are epsilon units away from L. That's always, you can get sufficiently close to L by choosing basically a good value for delta, a correct value for delta. And in the next video, I will show you how to find this correct value of delta, how to actually use this definition to make a formal proof of a particular limit. I hope you enjoyed, and hope to see you next video. Thank you.